Thank you all for coming. Today we have the pleasure of having a Tuve lecture given by Bob Stern. Bob Stern's well known to us, is particularly well known to me because Bob and I were students together at Scripps back when there were still dinosaurs roaming the earth. I knew and appreciated Bob then because he was one of the social leaders of the graduate students, both social and scientific. Bob has worked on many things throughout his career, but he was very much a leader in recognizing the fact that subduction in interoceanic plates is where you need to go to understand that process, plate subduction. Many looked at arcs, including people from Carnegie working in the Andes. It's a great place to work, but it's unbelievably complicated. If you want to get around a lot of those complications, Bob was the one to recognize that the oceanic system is much simpler, but much simpler relative to something that's so complicated you can't get it. So it's still a complicated picture.
Everything's relevant.
Yeah, everything's relevant. So Bob came to DTM after his Ph.D. at Scripps. He was here for a few years and then moved on to the University of Texas at Dallas, where he's been since. He's, as I mentioned, a pioneer in the study of oceanic island arcs and the whole process of subduction in general. He's also worked on some very interesting other topics, which he's around for the next 2 weeks, so please feel free to come and meet and talk with him about it. One of which is something that's, I think, missed in a lot of geology programs and earth science history in general. Is a large part of the eastern desert of Egypt is composed of granites, which is a typical rock of the continental crust, except these granites appear to have come directly out of the mantle, or at least have spent a very short time of residence in a continental crust. So there's a large fraction of eastern Egypt that in fact was generated out of the mantle in a very short time interval. So there are ways that the Earth knows how to make continental crust directly from the mantle in a short time interval, and Bob is one of the few people that has been working in areas where this is most pronounced. As I mentioned, his focus has been on the plate tectonics, and in particular plate subduction, which is going to be the subject of his talk today. Is how and when did plate tectonics start on Earth, what came before, and why does it matter? Bob, all yours.
Thanks. So you ready to, oh, we have to get me.
Gotta make them, what do you call it, wired up. Stick it in the pocket. Thank you. Oh, it's a real treat to be back at DTM, and DTM and the geophysical lab together is something that we dreamed about when I was a postdoc, and it's like, wow, it's amazing that it happened. And it's even more of a treat to be giving a lecture in honor of this great man. So I've got a lot of slides, and lunch club is not that far in the future. So let me get started, and I trust you guys will interrupt, and if I don't see your hand go up, just yell at me. I'm happy to talk about any of these points. So let's just start off with a perspective. Wonder how they got that backwards. I think you recognize them. But if we look at these 8 great silicate bodies in our solar system, we get an interesting story that sort of frames the problem that we're going to talk about. So Mercury, Venus, Earth, Moon, Mars. And then these 3 I don't think we can neglect. Once we talk about define what large is, then Vesta gets part of that, but Vesta, Io, and Ceres. So we've got 8 large silicate bodies, and 4 of the 8 are tectonically and magmatically alive. So, Mercury's dead, and the Moon's dead, Vesta's dead, and Ceres is dead, although these little bright spots are really intriguing. But 4 of them are active: Venus, Earth, Mars, and Io, and only one of them has plate tectonics. So that tells us, just looking around our neighborhood, that Earth is special. Only Earth has plate tectonics. Venus is tectonically and magmatically active. Mars is, Io certainly is, but only one of them has plate tectonics. So plate tectonics is unusual, and saying it's unusual in our solar system suggests that it might be unusual in our own planetary history. It deserves a very close look at when, how did plate tectonics start, what happened before and why is it important to the larger field. So,
Is that true historically, that no other planets have ever had tectonics?
well, that's a discussion point. We know of none, but
Mars has evidence for
Yeah,
perhaps
I've
some
heard
early
that. That's
existence.
why I said
That's the only obvious one.
yeah, no, Mars is controversial. So this conversation has been going on for a while. In 2006, we had a Penrose conference out in Wyoming, and a couple of DTM people were there. Steve Shirey was there, and Paul Silver's in here somewhere. Couldn't really pick him out. But in 2006, we only looked at this question of when did plate tectonics begin. And I think that discussion led to a realization it's a much more nuanced problem than just when. There's really four parts of it, at least as we see it now. When, how, what came before, and why does it matter? So just to give you an idea of how this discussion is evolving, I just looked yesterday at Google Scholar, just typed in that, when did plate tectonics start? There were 46,000 hits and 17,500 since 2014. The topic seems to be attracting more interest and from a very wide range of geoscientists. So here's a broad outline, and we're going to start first about what are the forces that drive plate tectonics. If we don't understand them, then we have no theoretical basis for continuing on this discussion. Then let's talk about why it is important to understand when plate tectonics began. I think we as a community owe it to ourselves to say, okay, how central is this controversy to our science? If it's not very important, then let's not waste any time in it. On the other hand, if it's as important as I'll try and convince you today that it is, then maybe this ought to be a focus of 21st century geoscientific research. We'll talk a little bit about the discussion of how did plate tectonics start on Earth, and then I will give you a very idiosyncratic and minority view of when plate tectonics started on Earth. Okay? And then very briefly we'll touch on this issue, what was Earth's tectonic regime before plate tectonics started. And then at the end I'll show you my favorite coin. Okay, so what drives plate tectonics? So we have now a profound understanding that plate tectonics is driven by the sinking of lithospheric, oceanic lithosphere and subduction zones. It's a mode of convection that is fundamentally driven by the sinking of oceanic lithosphere and subduction zones. And in a sense, a more accurate representation of our tectonic regime would be to call it subduction tectonics, because plate tectonics is a superficial expression of purely kinematic description of what the plates are doing. The dynamic description of plate tectonics is centered on how the lithosphere sinks in subduction zones. Okay, so here's Warren Hamilton's cartoon of it, and in it he emphasizes his point, which is the dip of the subducted slab, which is marked by earthquakes, is an inaccurate and misleading representation of what the slab is doing. The slab is sinking more vertically than the dip of the earthquakes would imply. And so that's why these big arrows of the slab rolling back. And in fact, we can see this very simply. The Atlantic could not open if the Pacific wasn't closing. The Pacific's surrounded by subduction zones. In order for the Pacific to close, all of those subduction zone trenches have to be rolling back towards the center of the Pacific. It's obvious. Warren was first to point it out. Okay, this is another iconic observation about plate motions. So this is Forsyth and Oyeda, the most important graph they plotted, which is plate velocity versus the percentage of the plate that's surrounded by the trench. So if you want a slow plate, of course put it on a continent, but that's not in here, but make sure that it doesn't have any subduction zones. If you want a fast plate, the faster you want it to go up to the plate tectonic speed limit, surround it with trenches. So the Cocos plate there is the fastest moving, and it's pretty much settled science. Now there is a role for plumes. We're not going to get into that in this presentation, but there is a role for plumes. Although, in terms of Earth's tectonics, plate tectonics, the most important player by far is the sinking of lithosphere and subduction zones. Now, this is just to put this in place. Here is sort of a column through a downgoing oceanic plate. So you can see 95% of that plate is mantle lithosphere. And the mantle lithosphere plays the key role because it provides the excess density that's needed to drive subduction. Now, if you're interested in volatiles, you're going to be much more interested in this part because most of the water and the CO2 is going to be locked up in the oceanic crust and perhaps the uppermost mantle. And so the volatile flux, you've got to focus on this part. And then, of course, if you're a geochemist and you're interested in rubidium and cesium and things like that, then this 0.5% of the downgoing plate is going to be the overriding consideration. All right, so with that understanding, let's just think about what, yes?
How much does it upset your model if one says that looking at the seismic stresses, sinking plates are not the driving force? Because you get compression outside the trench, not tension, which is what you should get if the gravity sinking was everything. But it's almost universally found that the stresses in the plate before it hits the trench is compression, and also that forebulge also indicates compression.
Well, the forebulge, as I understand it, is a locus of normal faulting that is there in order to allow the plate to bend. Bending 100-kilometer thick rock is not easy.
Yeah, but that's where you have to look at the rheology, because Holodene rheology, if you can get the strain rate up, the viscosity drops low. And if you look at the seismicity in places where you have a lot of contortion, like in northern Japan at the Hokkaido corner, you can actually see the stresses even don't follow the curvature, they follow the gravity pulling. Anyway, just to...
So I take your point, which is it's not quite as settled science as I suggested it might be.
No, that's right.
Okay, point taken. Okay, but if we consider an earlier Earth was certainly hotter, and so this is Pollock's heat flow map showing, okay, maybe interior Earth upper mantle had a 400-degree hotter upper mantle, you know, because of a much higher radiogenic heat production and leftover heat. The lithosphere would have been thinner. The mantle part of the lithosphere would have been thinner. That higher mantle potential temperature would have made thicker oceanic crust. The buoyancy of oceanic lithosphere in the early Earth would have been higher than it is today. If the sinking of the lithosphere is what's driving the plates, then it's logical to consider that the early Earth, it was more difficult for lithosphere to sink than it is today. Okay? Hold that thought in your mind, and the observation that I'd like you to take away from this is that this early Earth thermal structure would have worked against plate tectonics, not favored it. Okay, so let's move beyond that, and let's talk just about a few points about why it's important to understand when plate tectonics began. This is in many ways the most tractable, accessible part of the discussion. The entire community needs to chime in why it matters whether plate tectonics began the day before yesterday or began one day after the Earth was accreted. So let's just look at three simple examples. First, the question of continental crust. Is there more of it or is there less of it with time? Then the next question, how much water is in the mantle? And we could put CO2 in there too. And then, what about evolution? What about the evolution of life? Real quickly. So here is a present inventory of crustal production and destruction, continental crustal production and destruction by three people. So Peter Cliff did this first in 2009, then I and Dave Scholl did this a few years ago, and then Charlie Stern, unrelated, did it a year later. And so here are all the places where continental crust is produced. Most of it's being produced by arc magnetism, either in intraoceanic arcs or in continental arcs, but rifts and collision zones and other things. And then these are all of the places that continental crust is being destroyed. And if we take the various estimates that we can come up with, then we see that total crustal additions, according to these two studies, somewhere between 3.2 AU, where an AU is an Armstrong unit, cubic kilometer per year, somewhere between 3 and 5, and the total destruction is greater than 3 to over 5. So these estimates vary in detail, but they agree that the volume of the continental crust today is either staying constant or decreasing. Now this collides a bit with the favored models. These are 13 crustal growth models. Here is today. We have 100% of continental crust. Back in the past, there was much less, and the question is, how did that crust grow? But this all implies that the crustal growth mechanisms have been, by and large, the same over Earth history. What if plate tectonics takes off at some point, and since plate tectonics, continental crust has been decreasing, then the crustal growth curves, instead of being inside this envelope for the 13 accepted models, could have followed this. The Earth could have been completely encased in continental crust in the early Earth, and since that time we've been decreasing it. Okay, that's kind of a reductio ad absurdum part of the argument, but the point is that the issue of when plate tectonics began is central to really understanding how continental crust has grown, if it has grown.
But Bob, if you're not subducting crust, you're not making continental crust, if that's the prime site of continental crust production.
All of the planets have crust.
Yeah, but it's not going to be the same type, it's not going to be continental crust in the sense that you're showing it here.
Probably worth a Penrose by itself. All right, let's go on to another question. Is the mantle degassing or regassing? So I got, Eric Howard gave me this nice cartoon of sort of what's going on to control the natural CO2 deep cycle. Works just as well for water and other gases. And so you have mid-ocean ridges that are degassing, hotspots that are degassing, islet arcs and continental arcs that are degassing, back arc basins are degassing. The only places we're putting in water and CO2 are in subduction zones. So the question is, how much water and CO2 is down there, and is that increasing or decreasing? Is the planet degassing or regassing? Right now, you'll see a number of estimates for what the water's doing in a subduction zone, but this is Hacker's a few years back. You can look at other ones. And this is all of the fluids that are entering the trench, and most of it gets recycled pretty shallow. Some of it comes out in magmas, but quite a bit is recycled beyond 4 GPa into the deep, at least in the deeper part of the upper mantle. So if that's been going on a long time, the question is, why do we still have an ocean? All right, and let's finish up with biological evolution. So the biologists are quite interested in evolution of life, and what we see is between about 1.8 and 0.8 billion years ago, it's now being called the boring billion. And just to add on that, Buick and others called the time between 1.6 to 1 billion years the dullest time in Earth's history. In terms of environmental, biological, or geological events. It might be a little bit of hyperbole, but I think it captures the sense. But all of a sudden, evolution takes off in the Neoproterozoic. Why was that? So does plate tectonics play any role in that? I would think it would. We can imagine a world, sort of a daisy world, except I'm not good at drawing daisies, but so we have no plate tectonics, and so things do happen. You have meteorite impacts, and you have plumes. And so we have one kind of plant, and one kind of herbivore, and one kind of carnivore, and they sort of maybe evolve on land. Well, they mostly evolve on the shallow shells. And there's just not much going on to stress them to move forward much with time. But if you take a plate tectonic planet, and you break it up, then these will be isolated and will evolve in different ways. And then when they come back together, continental collisions, then there'll be competitions, and one of them will lead over the other. And you can imagine how a plate tectonic world with shallow shelves and continents would lead to faster biological evolution. one without plate tectonics. So those are sort of just three considerations off the top of my head about why we need to understand this question. It's not, and I hope there's many more, and I hope that we advance this discussion of why it's central to do this. All right, now let's just talk about how did plate tectonics start on Earth. So this is basically the question is, how did the first subduction zone start? So if we look at the question of how did plate tectonics start, we can answer this if we can figure out how the first subduction zone formed. So here's 5 ways to make subduction zones today. So induced means that there are plate stresses that are continued even after a boundary is destroyed. Here's a subduction zone, you get a collision, and then you get, I call it transference because the original dip is maintained but it's transferred outboard. And then you got polarity reversal, you have a collision and then the subduction zone changes direction. But there's already plate tectonics and all that's happening is a reconfiguration of the subduction zone. So this is not what happened in the starting plate tectonics. These spontaneous ones are situations where subduction zones start in the absence of plate tectonic forces. One of them is passive margin collapse. This is an iconic representation of what happens as part of the Wilson cycle. We have no Cenozoic examples of this, so this is, to me, is deeply suspect, but it's possible it could have happened. Transform collapse seems to me to be the dominant mode that we form new subduction zones today. The Izu-Bonin-Mariana was a system in the Eocene. This was a transform margin. You had young oceanic lithosphere next to old oceanic lithosphere. This one began to flex. You began to get downward sinking, not subduction yet, and then forearc spreading, which is where most ophiolites form, and then true subduction like we see today in the Western Pacific. This is the one that I'll explore with you briefly, is that when you have a mantle plume, you set up the conditions that could lead to formation of a new subduction zone. So if a mantle plume comes up here, it reactivates the lithosphere, and it potentially could cause that first subduction zone in there.
Excuse me.
Yes.
If you have a mantle plume, which is a fairly localized event, would you also consider a very large impact as possibly triggering such a thing?
This is Vicki Hansen's idea 10 years ago, and certainly impact is another way of rupturing the lithosphere. I think, but I don't know, that the impacts that were large enough to rupture the lithosphere over a large enough area only happened very early in Earth history. And so if we say that's the way it formed, then we basically said plate tectonics began in early Archean or something. But yes, that's certainly out there on the table. But let's take a look at a modern example that we just, Scott Wadham and I worked on. This is the Caribbean plate, and this arc here, this convergent margin, Central America, through Guatemala, El Salvador, Nicaragua, Costa Rica, and Panama, has been operating since the late Cretaceous, about 90 million years ago. And the question is, how did this subduction zone begin? So here we have a little more detail, all of the age information we have about going back into the late Cretaceous to the present volcanic arc there. So the Caribbean plate is kind of remarkable because single plate is mostly made up of a large igneous province, and it's flanked by subduction zones. So all of this dark green is oceanic plateau. It's thought to have formed in the Galapagos, over the Galapagos plume. This subduction zone is older. It seems to be formed in the early Cretaceous. Geology of Cuba is going to be one of the most exciting things to work on in the next few years. This one began about 90 million years ago, and it seems that the geologists are being asked to come up with an explanation how a plume could form a subduction zone. And Scott Wadham and I came up with this story that there was already the subduction zone operating under the Greater Antilles Arc, And then this Galapagos plume came up and weakened lithosphere, separated the dense lithosphere to the west from buoyant lithosphere above the plume, and it began sinking and evolved from a plume into a subduction zone. And with one modern example. So now we get into the controversial part. Okay, but you guys will bear with me, I know. Okay, so this is Koronaga's summary of a few years ago. Not exhaustive at all, but here's the geologic time scale. We're here 4.5 billion years ago. That gets us almost back to the beginning of the Earth. And here's 10 different estimates of when plate tectonics began. So Hopkins et al., and then that's the two troublemakers up here. Most people, there's Steve. Steve, I think you'd probably agree with that. Up to 3.2 somewhere. Yeah, so, but I mean, this is where, I think this is an accurate representation of where the most of the geoscientific community thinks plate tectonics happen.
You're not going to talk about the pole at the plate at the when plate tectonics started on Earth, Penrose. So Bob had this Penrose in Lander, Wyoming, and we started the Penrose with a pole of what people thought plate tectonics started. Then after the two-day conference, we had another pole, and what was the result?
The result was that at the beginning, it was only one person that started in the Neoproterozoic. That was me, and at the end, it was unanimous that it started in the Archean, but that was because my vote got miscounted. I got confused. The vote could have been taken while I was out of the room. Yeah, easily confused. You know how it is.
Forgot that. You forgot that.
But anyway, so what I'm going to present to you is a minority opinion, but I'm up here and you're not, so. All right, so I'm a geologist. I mean, I pay attention to what the theoreticians say because they teach me a lot about how the Earth works. But at the end of the day, I'm going to look at the rocks. And so here are 5 geologic proxies for when plate tectonics began. The idea is that when these things begin to appear in the rock record, the evidence for plate tectonics is strong. And so everybody has their own thing, knows when spring is coming to Washington because, you know, whatever the first flower is that you like or whatever the first bloom is. So a geologist will have a different list of, okay, spring is coming, plate tectonics began. This is mine. So ophiolites, this is widely accepted because this is the spreading, this is proxy for seafloor spreading. And then subduction proxies, blue schist and jadeite, and then continental collision proxies, ultra high pressure metamorphic rocks, and rubies. So, just to remind you, some of you may not know, everybody knows what an ophiolite is, right? Or anybody not? Okay, good, so we'll go through it. So an ophiolite is a sequence, an association of rocks that is accepted by the geologic community to represent oceanic crust and upper mantle that's placed up on land for study, which really works well for us because we like to breathe air for some reason. So as sediments, there's a certain kind of lavas, pillow lavas that have this very diagnostic appearance. Sheeted dikes, which demonstrate 100% extension, infinite extension at a mid-ocean ridge. And then the plutonic rocks, gabbros and ultramafics. And underneath them, a residue after melting of the upper mantle, tectonized peridotite, just call it mantle. It's a clear and important proxy for seafloor spreading and plate tectonics. So here's an example of people for scale. This is in Oman, and that's the moho, the boundary between the crust above and the mantle below. It sort of tells you how important these things are, that we actually get to walk around on the moho. This is Yildirim Dillik's compilation of ophiolites from 2003. We can update it, somebody should. And he stopped it, and he has a different opinion about when plate tectonics began. but he usefully stopped it for his purposes at 1,020 million years ago. There are a couple of 2 billion year old ophiolites. I think one, maybe you'll see one up in Finland. Burma, and then there's one up in northern Canada. They do exist, but by and large, if you want to summarize Earth's ophiolites, you start at about 1 billion years ago. And there's a bunch more of these that are on here, because these can and have been nicely dated paleontologically, and these as well. These, on the other hand, have to wait for good radiometric ages, which up until recently were very difficult to obtain. Yes?
Just out of curiosity, if we're looking at this type of crust as indicative of plate tectonic, I'm trying to envision what I'm comparing this against. What does pre-plate tectonic crust look like?
I plead the fifth.
I mean, is there any chance that what we're seeing, if we found a 2 billion year old ophiolite, that's pre-plate tectonic ophiolite? And if so, how do you distinguish that from your Neoproterozoic ophiolite?
The 2 billion year old ophiolites do exist. They're worth a talk in their own right. And but the point is, once you go back from this time, then you're very hard pressed to identify something as an ophiolite. So one of the most interesting problems that Science has had, Science the journal, is they've published a couple of papers on Archean ophiolites, and in both cases it was found to be wrong. One in China and one in Greenland, and it was slightly embarrassing. But I mean, when Science publishes an article on an Archean ophiolite, you just wait a few months, and there'll be well, that's not an ophiolite. It's really not. That's my prediction. So I didn't answer your question, but maybe at the end you'll get something like an answer. All right, let's move to subduction proxies. Blue schist. So actually all 4 of these left are metamorphic rocks. And so you can say, well, look, Bob, the problem with ophiolites is you have a little bit of erosion and it's all gone. So the older the rocks are, the more likely they've been eroded off. Okay, that's true. But for the other 4 things I'm going to talk about, blue schist, jadeite, ultra-high pressure metamorphic rocks, and rubies, erosion just exposes more of it. So the erosion out for the people that want to dismiss the geologic evidence doesn't work. And it's sort of been responsible for a kind of a rejuvenation of metamorphic petrology, because it's now such a central part of this kind of a discussion. So let's talk about the subduction proxies. Blue schists in blue triangles and jadetites in green squares. And you can see they're sort of distributed together. So around the Circum-Pacific, around the Caribbean, all through the Tethyan Belt, the Urals, they're basically, they fit together like hand and glove. And the neat thing about these 2 proxies is, on the one hand, the only people that care about the blue schists are the academics and the researchers. The people that are interested in jadetites tend to be people that are in the gem industry. They're just looking for more material that they can use, sell, or whatever. So these 2 different communities have different approaches, but they come up with the same basic answer. That's where the old subduction zones were. So these are the reason these rocks are so important is because they're only produced in these cold geothermal environments that characterize subduction zones. So this is a Van Kecken model of a subduction zone, and you can see the tremendous coldness that carried to great depth in the subduction zone. It's sort of characterized by this very low geothermal gradient of a few degrees per kilometer. And that's why you only get blue schist and jadetite down in those environments that are so characteristic. Blue schists are one of our most beautiful rocks. If you're ever in wine country, follow the Russian River out to its mouth at Jenner, and there are just some beautiful blue schists sitting there. Wonderful, if the weather's nice, to go take a look at them. The key blue element, the blue mineral, is glaucophane, which is a sodium-rich amphibole that gives it this distinctive color. Okay, so let's talk a little bit about jade and jadetite. This is the subduction gemstone, and there's 2 types of jade. There's nephrite jade which is, interestingly enough, a calcium-magnesium amphibole. It mostly forms in subduction zones, but there's some of it that doesn't. It forms around contact zones around igneous intrusion, so we're not going to worry about nephrite. The jadetite, as far as we can tell, is only formed in subduction zones. It's a sodium aluminum pyroxene, and it is the beautiful gemstone of subduction zones. So the jadetite, these occur as dikes, and it's some kind of a reaction between the fluids coming off the subducted slab and the overlying mantle peridotites, here shown by the serpentinites. So you get these complex reaction zones with jadetite in the core, and then albitite and chlorite, these very interesting reaction zones between the main fluid passage and the surrounding mantle. Okay, so if we look at all of the known examples of these two subduction proxies, blue schist and jadetite, that's what it looks like. So this is going back, it only goes back to 3 billion years. There's just no, it's a question of how skinny of a figure do you want. But we could extend it over here to 4.5. This is where they're found. They're mostly Phanerozoic, and they extend, the oldest blue schist is actually in western China, in the Aksu, 800 million years or so. Okay, those are the facts.
So Bob?
Yes.
So a way that you lose blue schist in the Archean is that pretty much every Archean crust or rock has been through at least green schist and amphibole grade metamorphism. So if it was a blue schist, it wouldn't be now.
And Kevin Burke once told me, "Oh Bob, if you blow on a blue schist, it turns green." So I take the point, but maybe not. I mean, there's a lot of lower grade minerals present in Archean rocks, and they are there. If they are there, they will be preserved, I think. But this is obviously retrogression is another consideration, especially related to blue schist. Now I don't know about jadeite. I mean, these guys, they're looking for these rocks. They don't care what the literature says. It's like these guys looking for uranium in the 1940s out in Utah. The geologist said, don't look for uranium in sandstones. And they went out with their Geiger counters and found petrified logs made out of pure uranium anyway.
But Bob, maybe the sodium is tied up in tonalite, in the Archean, and here at younger times you've got free sodium, which is really critical to making the sodic pyroxene.
There's ways out of the box. I take your point. It just seems to me the ocean's always been salty, and so there'd always be plenty of sodium in altered seafloor. All right, so let's move on to continental collision. So there's two proxies there. One of them, is really pure academic research. This field, ultra-high pressure metamorphic rocks, has really developed recently into a very important field of study, and rubies. So continental collision is implicit if plate tectonics is operating. So we have, these are all of the convergent plate margins on the planet today. And of course we've been talking about subduction zones, which surround the Pacific and the Indian Ocean. But as we go farther west in this old closed ocean, we have evidence of continued convergence in the form of great mountain ranges, the Himalayas, the Zagros, the Alps, the Vedic mountain belts in there. About 25% of convergent plate margins today are involving the attempted subduction of continental crust. And this completely upsets the density drive of the subduction zone, because the continental crust is more buoyant. It's a much larger part of the downgoing lithosphere. It's often associated with buoyant upper mantle, as in the case of the Indian Craton. And so when continental crust gets in a subduction zone, the subduction zone starts to slow down, and a lot of interesting responses happen. Eventually, the subduction zone will stop completely, although it's been 50 million years and India shows no sign of slowing down. But anyway, this is sort of a cross-section, and here we have We can think of this as India being subducted beneath Asia, and it's the Himalayas. And in this realm is where rubies form, and at greater depth where the ultra-high pressure UHPs form. So ruby is the collision gemstone. Let's take it first. It's beautiful, has been a beautiful rock for thousands of years. People have been looking for it. And it's basically just high-class corundum. Corundum is just aluminum oxide. It's got all kinds of other elements in it. Trivalent ions can easily substitute for aluminum. You'll have iron, titanium, chromium. Interesting, the word comes from a Tamil word, Kuruvin. Is there somebody that knows how to pronounce that better than I do? Kuruvindam. It means ruby. Corundum comes from the Sanskrit word for ruby. It's the second hardest mineral that there is. Only diamond is harder, and it's extremely dense. It's beautiful mineral even when it's not ruby. This is the one I.
Coloring agent, chromium.
Yeah. So a little bit of chromium goes a long way. This is. I was at the Smithsonian, and they had this beautiful specimen. I mean, just incredible. You just look at that, and that color is just amazing. Trigonal. Good mineral for teaching students about the crystal classes. So it's just a little bit of chromium will make otherwise unappealing corundum look like that, or a little bit of work like that. But how do you make this? How do you get a little bit of chromium in almost pure aluminum oxide? Well, it's a geochemistry problem, but here's the best way to do it. What you need is a dominant system that's aluminum rich and silica poor, for example, shales or carbonates juxtaposed. And then you need to get the chrome in from somewhere, which is going to come from serpentinized ultramafics. And so this kind of an environment where you got some kind of ultramafic rock, serpentinized ultramafics, which are chrome rich, not too far away from a sequence of shales and carbonates, or fluids can interact under big pressure. You can do that, and you get that in what we call passive continental margins, which we're very close to here. So here's Washington, D.C., and if we go out to the east, we get the Atlantic Ocean. But before we get into the deep water of the Atlantic Ocean, we go through this thick sequence of sediments that was deposited here for the last 180 million years, basically from erosion of the continent. But the rivers don't carry the muds and things out very far, and they'll be, closer to shore beach sands, more deltaic deposits, and farther to shore cherts and pelagic clays. And in this very thick sequence here, you'll have lots of shales and carbonates. But so here the shales rock, the aluminum-rich rocks that we can make our corundum out of, the chrome is down here 40, 30 kilometers below it, down here somewhere. So how do we get the chrome-rich rocks up with the aluminum-rich rocks? And the best way to do that is in this kind of an environment, where you carry the passive margin sediments. Imagine that passive margin is sitting here, just at the leading edge of the continent. And in this region here, you've got ultramafic rocks, very close juxtaposition with aluminum-rich sediments. So that's where we form rubies, in those parts of the subduction continental collision zone. So let's go a little bit deeper and look at UHP formation. Now, ultra-high pressure metamorphism is, as I said, one of the really interesting developments in the field of metamorphic petrology in the last few years, because what they find to be an ultra-high pressure metamorphic assemblage, you have to either have diamond, preserved here in a nice garnet, or coesite, partly retrogressed here at quartz. The diamond, everybody knows, pure carbon. Coesite is a high-pressure silicon polymorph. And to reach these, you have to get to depths of 90 kilometers or more deep in the earth. So these, all UHP terrains, are clear samples, are samples of continental crust that are deeply subducted and then brought back to the surface. So these are PT paths for the major metamorphic facies. Blue schist we talked a little bit about, and phyllite we haven't, but it's a very low pressure, higher temperature realm. Green schist is higher temperature, lower pressure. These are common assemblages that are not diagnostic of plate tectonics. Blue schist and the UHP realm, which is defined here by the quartz coesite boundary or the graphite diamond boundary, are. So here are sort of three trajectories for a UHP, one that doesn't go very deep and then comes back to the surface, and one that goes a little bit deeper, still doesn't make diamond, and then of course one that gets all the way down and makes diamond and comes back up. So it's really quite remarkable that things can be carried so far deep into the earth and brought back to the surface in these collision zones. This is a map of all of the known UHP examples. So this is from Tatsuki Sujimori. So these are coesite bearing UHPs, the red stars, and a little bit down there, and the world's youngest one. And then these are the diamond bearing UHPs in the Alps and Norway, a little bit there in Greenland, and then some over here in Central Asia. So these are very difficult things to find. They require concentrated effort, real skills with a very wide range of analytical techniques. But there's a lot of people looking for them, and that's where they are known to exist as of today. Probably there's more, but probably that's also sort of outlining the most important occurrences of them as well. This is the age histogram for the two continental collision proxies. So Ruby, most of them are younger than 600 million years. There's one at 2100 and one at 2800 up in Greenland. And then the UHPs, they're all younger than about 650 million years. So those are the continental collision proxies. They're overwhelmingly younger than about 700 million years old. Okay, so let's finish up with this last part, which is, okay, now we've opened up the imagination space to say there was something before plate tectonics, and we're going to argue for quite a while about when that happened and how it happened. But if we do say that there was this time, then there had to have been something before, right? Move wrong way. So, it almost certainly was some form of stagnant lid. And stagnant lid maybe is an unfortunate term, but basically what it means is the lithosphere is one piece and it completely surrounds the planet. So you can have active stagnant lid and you can have dead stagnant lid. So let's take dead first. I think everybody knows what that is. There's no tectonic or magmatic activity. The surface of the planet looks like it's been beat up. Mercury, Moon, Vesta, definitely. Ceres, the jury is still out on what those little white spots are telling us. I mean, superficially that looks like a very dead asteroid, but why the hell do you have white spots? I mean, it's one of the most interesting puzzles I've seen in a long time. And then, of course, active stagnant lid. There's lots of tectonic and magmatic activity. So Venus is an extremely active planet. It's just doesn't have plate tectonics. Mars is, it fires off every once in a while, but it's another one. Io, now that's an interesting one. It's a fairly small silicate planet, but it keeps getting flexed like a tennis ball by the gravity of Jupiter, and so it's much more active than its size would have led you to believe. But these are three different stagnant lid, large silicate bodies. And Io seems to be a heat pipe planet. These little pimples are little volcanoes. What seems to be happening is just magma's coming up, erupting, and then there is a crust and there's a partial melt zone down there that this crust keeps sinking into and getting reworked. And so that's one style of stagnant lid, sort of heat pipe stagnant lid. And Venus seems to be sort of plumes and drips. So you've got regions where you've got mantle plumes, maybe that's one. And then places, in order for the mass flux to go to the surface, there has to be some place that it's going back down, and it seems likely that that would be some kind of a lithospheric delamination or dripping or whatever. And then Mars seems to be sort of one big complex plume centered on the Olympus Mons, some rifting. But these are sort of three little samples of different active stagnant lid. And we would have never predicted these without having observed them. And so now when we try and say, what did Earth stagnant lid look like, our imaginations are our only limitation. And then the geologic evidence, how will we recognize any of these styles in the geologic record? Absolutely. It's a huge challenge. We need more silicate bodies so we can expand our roster of what stagnant lid looks like. But just that look tells us that there's a wide range to this thing that's encompassed by stagnant lid, which doesn't sound very exciting, but clearly is. Okay, so this is one way that the Earth could have evolved. So I think everybody agrees that early Earth had a magma ocean, and maybe it was at the surface and maybe it was at depth, but this probably developed some kind of a crust and then partial melt underneath it, and probably we had some kind of a heat pipe stage. And then we can imagine that the stagnant lid, early stagnant lid to late stagnant lid, first we'd have smaller drips and plumes and more of them, and then later we would have bigger drip delaminations and plumes, and then ultimately evolving to plate tectonics. And so that's one possibility. But once we say that plate tectonics began sometime in the past and start to address the issue of when and have a very broad discussion about it, then okay, let's figure out what this was, because that's just something, you know, give me a few beers and a half hour of my illustrator and I'll come up with something. It may or may not have something to do with the truth. But there is that sort of progression implied from thin, weak lithosphere to thicker and stronger lithosphere as we go from magma ocean or heat pipe to plate tectonics. So just few words about where we are. This is actually the beginning of an exploration that will go through 2015 and 2016. So there's going to be 4 different venues where we're going to address these issues. So the Gordon Conference is going to happen up at Mount Holyoke, interior of the Earth, surface connections. There's going to be a session on Wednesday morning, origin of plate tectonics. If anybody's going to that, Gordon, then we can pick up this discussion there. There'll be a whole morning devoted to it. Then Geo Berlin is celebrating the 100th anniversary of Wegener's publication of his book, his seminal book, in Berlin in early October. And we've got a session, when and how did plate tectonics begin on Earth? And in fact, that abstract deadline has been pushed back. If any of you are interested to participate in that abstract deadline is 18th of May. And I encourage any of you that want to attend that. It's going to be a really, I think it's going to be a really good meeting. We've proposed a fall AGU union session. When and how did plate tectonics begin? What came before? And why is this controversy important for understanding the Earth? We think this is a controversy and a discussion that needs to reach the broadest possible parts of our community. And so we think that fall AGU union session is the way to do that. And we don't know about that yet, but we're optimistic. And then we've been approved for a week-long conference in Monte Veritas in Switzerland on the origin and evolution of plate tectonics, which will be in July 17th to 22nd of 2016. So encourage, this one is already closed, this one is still open, this one hasn't been approved, this one we haven't advertised yet, but we will. Keep your eyes open if this discussion interests you. It's one that anybody at any level of your career can contribute to, and we hope you do. And I want to just finish up with one thing. because we're struggling now, I think, in a lot of ways in science. And sometimes it's because people don't remember what this country was founded on. So this is take you back to 1792. The United States had just formed, and the most important thing that any country does is money. So the first coins of the United States of America were coined in 1792, and they were the penny and the 5-cent piece called a half-disme. And the half-disme was purportedly made from melting down Washington silver. So you can imagine the importance that the leaders of the fledgling republic put on the first model they put on the United States coin. This is the first model that was put on the United States coins. And it only appeared in 1792 because it was just too long. The half-disme in particular is a very small coin, so you couldn't get this. But Liberty, parent of science and industry. That was our nation's founding fathers' motto. I don't think industry is doing too bad nowadays, but I don't think we've ever seen science in the United States under such concerted attack as we see today. And I encourage you to get involved and try and remind and notify people that you know that our founding fathers, the first word they put after liberty was science. Thank you very much.
Well, you're giving Bob a lot of grief, but let's continue.
Yeah, mineralogical grief, because you've chosen ruby and jadeite, which are rather unusual minerals, but there's a vast and growing body of information that during the supercontinent cycle, during collisional orogenies, there's a whole suite of minerals. Of course, zircon, which shows episodic, but the minerals of boron and beryllium and copper and cobalt and tellurium and mercury, and the list goes on, and you see this pattern with the assembly of Pangea. You see a certain geometry and distribution of the minerals. You see the exact same pattern with rhodinia. You see it with Columbia. You see it with Caterland. So how can you have these episodic events of mineralization if you don't have collisional dynamics?
Okay, so the thing that I think you might be referring to are these plots of zircon ages with time that show these tremendous peaks at 2.7 billion years ago,
That's one of
and
many.
1.9, and then a smaller one since.
1.2, yeah.
Okay, and this has been argued by Hawksworth and co-workers to indicate supercontinent cycles. Okay, so in that sense, then the collision of India with Eurasia should shed vast amount of zircons of 50 million year old age. And if you go to either the Indus or the Brahmaputra or the Ganges Delta and scoop up some zircons, they will be overwhelmingly 2.7 and 1.9, and the 50 million year and younger event will be negligible. There will be some.
Time for the erosion of the deeper area, that's where the photons are. They're more deep.
And this is where I think Hawksworth and people that think along these lines have just made a fundamental error in thinking. They're so driven by their models that they can't stop and look at the data. And the data are that when we collide continents, we lose continental crust. And a lot of it, we don't make continental crust, or very little. So I feel very strongly on that point. I mean, it's just like, what are you guys missing? Like, okay.
I mean, I think you've presented a very strong case for modern plate tectonics to give us an array of proxies and assemblages that we don't find in the old record. But what you didn't really say is in the old record we have a lot of lateral accretion that's been imaged by geophysics in lithoprobe and in the Canadian Shield that clearly show subduction-like tectonics in the shallowest crust above the moho. We don't know how deep that went, and we don't know what was sheared off between the crust and the moho. So we don't know really how to make it the same geometry as your modern assemblages. But there's no question that by the Neo-Archean, we have lateral continental assembly of large tracts of stiff slab. And that's missing from your timeline. So we may have a difference here in the two types, but there's no question we have subduction-like things starting to appear in the Newarctian, I think from the surface structural geology. You have
Yeah.
a lot of subduction rocks that are made in crustal differentiation as well.
Yeah, the lithoprobe profiles do show dipping reflectors. And then the question is, can that only be explained by modern style plate tectonics? There was clearly something going on that was the closest approximation to plate tectonics that we see at about 1.9 because it produced ophiolites. So that can't, and then with a little bit of ruby in it.
So let me follow up with a corollary question. So in the subduction zones today that are clearly subduction, that don't show us ophiolites, or don't show us blue schists, or don't show us jadeite, or don't show us ruby, of which we have plenty of examples, is that not subduction?
But look at the global situation. If you look at the global map, not just this field area or that field area, and you look at everything that we have on the planet, and now we're in an unparalleled time when we can do that because everything's being put in a database.
Right.
And so we look at the map and go, let's look at the whole planet. And are there blue schists at this interval? Or are there, whatever the proxies are? And I think you have to sort of, because there's no question that these things, not all subduction zones make blue schists or bring them to the surface. The whole process of bringing this stuff back up is, worth a couple of lectures at least.
Right. I mean, maybe we're looking at a transition between continent formation versus continent destruction, with the processes being more similar than we think.
Yeah.
A transition between those two type of regimes.
It's possible, but I mean, I'm going to defer to the geologic evidence. If I'm having to deal with all of the different lines of evidence for this discussion, there's theoretical, there's geophysical, I mean, you name it. But I mean, at the end of the day, the thing that I'm most comfortable with, and I believe in most strongly, is the geological evidence. Why would anybody want to believe geophysics over geology? Sorry, Simon.
Zach, did you have a question?
Yeah. Is there a way you could correct for sampling bias in your histograms of jadeite, ruby?
No, I don't think so, because these are sort of a representative sample of people who have been looking for jadeites and rubies for a long time before plate tectonics was worried about. And these, jadeite and rubies are where you find it. And the question is, are there other subduction proxies that would require a different approach to identify them? And you can imagine the UHP trail is a really specific one. The UHP community now knows where to look. And the problem is that's the only place they look. It's like the drunk looking for his keys under the light post, right? The light's best there. They're not looking for them in Wyoming because nobody's found them, but maybe somebody does, and all of a sudden, we get them. So,
I just mean, like, as a non-geologist, when you show a histogram going back 3 billion years, and if there's a lot of samples from the past 1 billion years, I don't know whether that's normal for continental.
but remember, these two different communities, and Steve will agree with me, the economic community has got a fundamentally different way of approaching, say, kimberlite, finding kimberlites and diamonds. They'll listen to us, but they're really not they don't think we have anything, well, Steve accepted, have much to help them with. They know how to find these things, and it's completely different than the way we go after our science, which is, I wonder where the UHPs are. And so involving that community, their minerals in this discussion gives us sort of a check on these academic, like ophiolites and blue schists and ultra-high pressure metamorphic rocks. That's the academic research community. But rubies, diamonds, jadeite, that's the economic, those guys are, and I use guys sort of Californian, so. Anyway.
John?
Is there a good reason that the proxies have to stay the same throughout the Earth's history? For example, the UHP diagram you showed was controlled by a critical geotherm for this forbidden zone, which is obviously controlled by the thickness and the speed of the slab. If that moves, then the proxies change. So maybe what you're arguing for is not.
No, that's an
Your
interesting.
lack of proxies before 1 billion years ago.
No, this is an interesting point. So, one of the points about blue schist, the traditional objection was, well, the Earth was too hot to make blue schist, right? But if you think about the thermal structure of a subduction zone, it's controlled by the thickness, the age of the lithosphere, and its rate of injection. So, in fact, you could imagine thicker oceanic crust in an Archean subduction zone generating more blue schist because it's being injected faster, and you have more. You don't make peridotite in blue schist; those are basaltic rocks. You have more basalt. So I think we do have to think about our prejudices about how these things are generated. Your point about are there other proxies? Absolutely, and I think
Do the proxies even stay the same throughout the history?
that's a discussion we haven't had, but I think it's a good one. What would an Archean subduction proxy look like? Now, one of the points we have to make is that the isotopic evidence is very clear. There has been return of surface materials to depth since the Archean at least, maybe the Hadean. There's no question about that. The issue is, does it have to be subduction? Is that the only way you can get surface to depth? I don't think so. I think those drips could do it too.
Interesting question whether subduction is a semantic word and there's more than one way to make a plate go down. Donald, do you have a question?
Done more or less asked the same question.
Are there any more questions then? If not, Bob's around for a couple of weeks. He's over in the cyclotron building. He likes to talk. He's very good at conversation, and he's obviously got a lot of background knowledge that I think a lot of you might want to share with. So definitely stop by and see him and have a chat. Thanks again, Bob.
Thank you. No, thank you. Well, I mean, it's one of the question was time, but it's such a